Okay. Yeah, I guess we can get started. So today I'm going to be presenting about model-agnostic meta learning. Um, and basically, in addition to model-agnostic meta learning, I also want to talk a little bit about multitask learning and few-shot learning, which is kind of related to like MAML. And to really appreciate like the results of MAML, it's kind of important to like understand like this background of what really multitask learning and few-shot learning are, and how that fits in like the overall like scheme within overall like ecosystem of ML. So yeah, let's get started with multitask learning. So right now, the current state of machine learning, right? You have a very over-parameterized model like InceptionNet on the right that's trained on one specific task, right? Like when you're training an ML model, you're training it to classify images, or you're training it to like analyze the sentiment of text, and it's on one specific task. You usually use a lot of compute, you train on a ridiculously large amount of data, and you beat benchmarks through deep learning. So this is like the classical like machine learning that happens in industry today. But training on one task, given all these constraints, can sometimes take multiple weeks. Now imagine doing this for 20 different tasks. It'd take years to train agents, right? And also, like generally, researchers want to create like agents that are more intelligent, right? That aren't just like, oh, let me overfit to this training set so that I can like classify dogs from cats. They want to build agents that are more intelligent and that can generalize to other tasks. So basically, that's what multitask learning is, right? So multitask learning is generalizes learning beyond tasks. So at the very core of it, you train a combined model to perform well on several, perhaps unrelated tasks, with the hopes of generalizing parameters across them. So this is a biological inspiration, right? So you have like your senses that go into your brain. Your brain learns some visual representation of objects, some auditory representation of objects to do different tasks, like eating beans, studying for 61B, or driving a car, right? So you have one combined model that's able to do a variety of tasks. So what if we took that and applied that to machine learning, right? So now you can classify beans as well as classify dogs using one combined model and do multiple tasks. So this is really what multitask learning is, right? You are having multiple data sets that go into the same model and is able to do multiple things. So multitask learning allows you to inductively transfer knowledge. So what this means is that it basically improves the model by introducing some kind of bias, right? So some bias is like inductive bias is when you cause a model to prefer some hypothesis over other hypotheses. So multitask learning introduces inductive bias by providing auxiliary tasks. And an auxiliary task is just a fancy way of saying like a secondary unrelated task to the main task at hand. So if you're actually trying to do dog classification, you feed it other images so that it can better understand how images themselves are able to be represented. And yeah, basically like this is just a very simple way of saying it, right? Like you just have some bias towards some like for example, like if you're doing regular machine learning, Lasso biases the optimizer to prefer sparse solutions over unbiased optimizer. And basically you're just extending that idea into multitask learning. So now it's able to learn auxiliary tasks as well. So how does this pertain to MAML, right? So basically you have like this huge parameter space, right? And you have some initialization, which we call P sub 0 over here of the parameters. And then you do gradient descent. So for example, if you're trying to classify dogs, then you like take some gradient descent steps and then you converge on like the optimal solution P sub dog star, right? But then what if you have another task like classifying beans, right? So how do you like create some way to like easily adapt your model to multiple different tasks? So this is what MAML does, is it tries to find a place in the loss landscape or like in the parameter space so that you can easily adapt your parameters from classifying dogs to classifying beans, right? So by having, so when you're in this space over here, you can just in a few gradient update steps, reach the optimal solution for either case. So that's basically how MAML works from like the very like in a very simplified way, just so you guys understand like why MAML is like important. So the reason why multitask learning is cool is because it massively grows the viable data set for a task, right? So let's say that you're classifying dogs, right? When you're classifying dogs, you only feed it dog images and it overfits to how dogs, like any like artifacts that are there in the dog data set, right? But if you're actually a human, you're not going to really like learn how dogs look like the way that CNNs do. You have some more general way to identify images, right? And from learning how images are generally, from that, you're able to like use extra like fine tuning to perhaps classify a dog. So this is basically what like multitask learning is. So when you train a dog classification network, multitask learning essentially allows us to learn from other types of images as well, because the low-level image features need to be learned for all the tasks. So by adding these auxiliary tasks with huge data sets, right? So let's say you're training like dogs versus cats. If you pass in all of ImageNet and if you pass in like millions of images, you can have this model learn from these millions of images, even though it only has to do dogs versus cats, right? So this is why like multitask learning is really cool, right? Is because you can basically like immensely grow the viable data set for the task and really like decrease overfitting as a result. Yeah.
How does this compare to like SSL or unsupervised learning is like your pre-training?
In what way? Like,
I guess like it sounds like the purpose of both is the same. Like you find a better like initials, like starting like set of weights, like performance and like downstream tasks.
Mm-hmm.
Does this like, yeah, I guess like, is this better than just like taking like a large like noisy data set and like learning visual features, or yeah?
Yeah, so actually, so I'll get to that later in the presentation, but basically like right now, like something that we do is like we have like ImageNet, we pre-train it, and then like from there you fine tune right on a specific task. So the thing is, in the optimization objective, there's nothing that like actually optimizes it for you to like fine tune it directly, right? Like you're just assuming that once you've pre-trained it, that maybe it's closer to like the actual like lowest point on the loss landscape, right? But if actually, when we go to MAML, you'll see that in the optimization objective, it accounts for the fact that we're able to take a few like fine-tuning, like gradient descent steps. So based on that, the optimization objective is different. So it might find like a more optimal solution to like fine-tune from.
MAML might also be seen as a way to make that transfer learning two-way. So normally you would just like, if you wanted a better like central model to fine-tune the different things, you would just put together a better benchmark, but that's hard. So how do you take all of the task data that you're fine-tuning this model on, and then make that like improve the original model? Is, I guess, like one way of framing it. I don't know.
Yeah, that makes sense. And yeah, basically multitask learning forces the model to focus attention on finer features, or this is at least what's seen empirically, right? So if you have like a large amount of data, especially with like CNN, sometimes it might just like only learn the features that are like very apparent and obvious in the image. So if you're trying to like classify apples from oranges, for example, it's mainly probably just gonna look at the color, like red versus orange, right? But there are also other features about the fruit, like for example, the stem or like the texture, which are less like present in the image, right? But basically by doing multitask learning, like in these other tasks, these other features might be important, and that like importance placed on other features transfers over indirectly into like the main task. So that's why multitask learning like forces the model to focus attention on finer features. So this is the reason why it like generalizes well and like overfitting is like decreased as a result. Yeah. And yeah, this is also kind of related. It's basically just like eavesdropping between related tasks. Like if you have some task A and task B, which have very different loss landscapes like this, right? So all this is like you have some, like this is the landscape for the loss, and you're trying to do gradient descent and you're trying to find like the like a minimum. So if task A is like very jagged, for example, and to learn some feature, it's really hard in task A because of how jagged it is. But in task B, if it's easy, by having multitask learning, you're actually allowing task B to find this feature F really easily and have that transfer over to task A. So there are a lot of reasons why like it might be hard to learn a feature for a specific task. Like the data distribution makes it hard to learn F, or there's like a complex non-linear relationship that takes a lot of training time to learn F. But basically, this is why also you can see like a speed up in like converging of the loss when you have like MTL for a specific task. Yeah. So basically to kind of understand like all these different like multitask learning methods, which by the way, we still haven't gone to the MAML paper yet. I just want to still contextualize like how MAML is important and how it like fits into this whole idea of multitask learning and few-shot learning. So there are like a lot of methods, as you can see here, that are related to multitask learning that have been developed over like the past few decades, both classical and deep. And I won't be really getting into too many of them. Maybe just like, I'll just go into like one or two of them just to get a like flavor for how like multitask learning works. And like a very basic one is just like normal linear algebra. It's called L1 LQ norm regularization, which basically helps you disregard entire features. So basically you take the L1 norm and then you take the LQ is just basically you can take either L2 or L infinity norm, which by the way, if you guys haven't taken like a linear algebra class yet, all an LQ norm, this is an LP norm actually, is you basically some power of the elements, and then that sum you just like take the 1 over p exponent of that. So like the L1 norm is literally just adding up the absolute value of the elements, and then the L2 norm is like it's like the Euclidean distance, right? You square all the terms and then you take the square root. So basically that's how like L1 LQ norm regularization works. It does something called block sparsity, which basically sets entire rows in the matrix, parameter matrix, to be set to 0 instead of individual parameters, so that this disregards entire features. And this is a very classical method, right? Like this is something that doesn't require like actually any ML at all. This was used several decades ago, and this allowed for multitask learning to work because like it disregards features that are specific to one data set. And there's also another classical method, which basically you learn the task relationships. So, and again, you don't need to like really understand the math or anything here. The main thing to take away from this is that in multitask learning, they're trying to learn the relationships between different tasks, right? So you have like some set of like, let's say 100 tasks. One is classifying cars from trucks. One is classifying cats from dogs. And some tasks are more related to others. So basically you're trying to learn what is this like hierarchy of tasks? Like what are the clusters of different tasks? And once I know this like inherent like hierarchy and structure of these different tasks, then this gives me information about what kind of features are really needed, right? Like if I'm classifying a lot of different types of vehicles, then maybe we can use this information to have the model like identify vehicle related features instead of just like car specific or like truck specific, right? So basically by learning this task hierarchy very vaguely allows you to like learn how different tasks are related, and from that build a more like robust model. And yeah, basically like there's also like this can be extended to deep learning, right? So there's a paper called Deep Relationship Networks, which basically in multitask learning, like there's kind of like two paradigms. One is where you have like the beginning of the model over here shared between multiple different tasks, right? So you have this like CNN, which these are all the convolution and like pooling layers. And basically they learn like these general features across these different tasks. But then here you have these different fully connected layers for different tasks, right? Like task 1 through T. And then basically what this paper does is it applies a matrix prior into every single one of these like fully connected layers. So by applying this prior, it's forcing all of these different tasks to kind of learn something in common, specifically this prior, right? So that more features are being able to be learned. So that's basically how like this works, and the like details of how it works with like different like Gaussian distributions and stuff isn't really that relevant, right? Because the focus of the reading group is on like MAML, but just so you get a flavor of how like multitask learning really works. Basically, you have like your combined model in the beginning, and then you like branch out to different tasks at the end. So yeah, there's so many like different like deep methods that are there. Like it's not really worth covering them in detail because a lot of them are outdated, and like there's there are like new innovations in the field every day. So yeah, basically just a few like these are some things that you might see like in multitask learning. Like a very easy one to understand is weighting losses with uncertainty. You just weight the loss of each task based on the uncertainty of the model for that task and how difficult that task itself is. So that's like a way to do like multitask learning. And yeah, before we conclude like the multitask learning part, some final notes are that like this is kind of like what you should take away for what multitask learning is that classical multitask learning basically projected all the knowledge of these task specific models into a constrained parameter space and created a unified model. So what that means is that you have dog and cat classification, one model for that, and then you have like car versus truck classification, and you have a model for that. And both of these models by themselves are kind of overfitted to the data set. So if you ask the car versus truck classifier to classify a van, for example, it's going to be very confused. So instead, what you do is you ask all these models to project all that knowledge into the same space. So that means that every single model has to operate on the same parameters. And as a result, they are forced to learn more general features. But in deep multitask learning, you see this trend of allowing each model to have its own parameters, but then you learn how the tasks interact and what's like the structure and hierarchy on top of this. And yeah, basically like MTL just forces the model to consider features that it may not consider that important, right? So like apples versus oranges, and if apples are red and occupy a majority of apple images, the model highly weights the redness of a fruit as evidence of an apple when things like the stem and the texture are not considered that much. So that's basically how like multitask learning works and like some things that you should take away from that. So before we move on to few shot learning, do you guys have any questions about what was discussed so far? Okay, if not, now we can jump into few-shot learning. So the reason why few-shot learning exists is like basically modern deep learning tells us to shove an ML problem with more data when accuracy isn't high enough, right? Like ImageNet has approximately 1.2 million images for an image classification task. But if you think about how a human learns, did we have to stare at 1.2 million images to tell dogs apart from cars? No, right? So that means that there might be something wrong in, or at least like first, like if our task is just to be really good at classifying one type of image, then yes, this is a perfect solution, right? Because we really want to find specific things about cars versus trucks. But as if you have the like idea of building like more general intelligence, right, that's able to adapt to a variety of different tasks, then deep learning may not be the best thing to do, right? So that's where really few-shot learning comes in, right? So instead of training on like millions of images, for few-shot learning, you actually sometimes train on like just dozens of images, sometimes like one image per class. And you might think like, how does this make any sense? Like, how can I train a model with only one dog picture and one cat picture and have it like be able to generalize to dogs and cats, right? And this is the like kind of the beauty of few-shot learning. So supervised learning is very prone to overfitting, right? So in Sci-Fi 10, we force the model to optimize for 10 classes of images, but if we ask the model about 11th class, it'll be clueless, right? Like it'll have no idea, like it'll be very confused and like it'll be almost random in its prediction. But few-shot learning is about learning to learn. And you'll see that the output of like a few-shot learning based model will actually is very generalizable, so that if it's confused about what a new object is, it's actually truly confused about it. And like it applies knowledge that it has to like any unseen data. So before we're going to get into how that works, like just some like terminology. So instead of a training set with a lot of data points, in few-shot learning, we have something called a support set, which is basically the same thing. It's just that you have a few data points per class. There's something called like one-shot learning. One-shot learning is where you just have like one data point per class. Few is like 2 to 3, 4, whatever, and like yeah, that's basically what that is. And then you query the data on the support set to find the most similar class. So basically what happens is the model tends to learn about how to recognize similarities and differences between objects instead of directly recognizing a fixed set of objects, right? So instead of learning the differences between apples versus cars versus trucks specifically, it learns what differentiates an apple from a truck, from a car. Like what are things about an image and things about objects that I can learn that allow me to like extrapolate that knowledge into classes I haven't seen before. So a very, very basic like few-shot learning implementation can just be done using like neural networks and like stuff that you already know. So for example, here you have a parrot and an elephant, and basically you want the model to output as a 1 if they're like the same thing and 0 otherwise. So what you do is you have a CNN here. And you have a CNN here. And basically, it's trying to convert the image into a vector, right? So it's trying to find some vector representation that encapsulates what a parrot is and what an elephant is. And then you combine it here, and then you have some dense layers. And then from this, you have a sigmoid function that outputs between 0 and 1. 0 is if the objects are the same thing, and 1 if the objects are different. So it's basically a similarity function, right? Like a very like simple way to, even without all the dense layers and everything, is just to do cosine similarity, right? You have two vectors. Ideally, if both are parrots, then you want the vectors to be in the same direction. And if they are, then the cosine similarity will be 1. But if they're different, then it'll be lower than that. So you can do very like basic few-shot learning just through like, this is called a Siamese neural network, right? Because you have a neural network for one image, neural network for another images, and they combine at the end. Yeah, and basically few-shot learning is a step in learning to learn. So that's what meta learning is, and that's why in MAML you have model-agnostic meta learning. Meta learning just stands for learning to learn, and few-shot learning is very related to this. So yeah, there's like a lot of like terminology thrown about, but these are all like kind of in the same like field of ML. And yeah, few-shot learning is notable because the computer is able to identify a new object by similarity to objects in its knowledge base with only one or a few support points per class. So this is like innovative in and of itself, right? Because previously, if you're doing image classification on ImageNet, you needed 60,000 images to like really recognize the difference between one class from another. But now you're able to do this with one or two images, right? So that in itself is like crazy. So when you train the model, the CNNs learn what features allow us to differentiate between classes of objects, right? So you learn the texture, shape, and color rather than or over whether there's like a stem, right? Instead of overfitting to something that might only apply to apples. And yeah, so now that we kind of understand multitask learning and few-shot learning, we can kind of get into like the paper that we wanted to present today, which is MAML. So yeah, before we do that, does anyone have any questions? Okay, if not, oh yeah.
Oh, one thing I thought I should mention is like, did MAML originally, like what field of ML did MAML originally come out of?
Like a meta learning. I think so. Like so meta learning is like the.
But like, what kind of tasks was it applied to originally?
Oh yeah, so in the paper they applied to supervised and reinforcement like learning. Gotcha. So yeah, I'll have that in future slides. But yeah, so now we can kind of delve into.
Just out of curiosity.
Yeah.
So, like, for these like few-shot learning papers, like where do you know approximately like what year they were released in? I was curious about like the relationship temporally with like some of the contrasted bosses that we've seen recently.
Yeah, so I didn't look at too many few-shot learning papers directly, but I think they're like kind of, it's like a more recent development. Like I think in the last like 4 or 5 years.
Yeah.
If I'm not wrong.
Siamese nets have been around since like the 90s.
Yeah.
And yeah, few-shot learning, it has only been around recently, and I think like the general idea of contrastive learning has only been around pretty recently. Right?
Mm-hmm.
Yeah.
Yeah, and actually like multitask learning has been there since the 90s too, especially like classical methods and stuff. Yeah. Okay, so with that we can get into MAML. So what are like the downsides of like current multitask learning methods in this space? So yeah, and to like appreciate the results of MAML, it's important to recognize how like multitask learning fits into the big picture. So in multitask learning and MAML, and just like in a lot of like current modern machine learning, how does it work? Basically, you pre-train a model with parameters that can be well adapted to a set of tasks, right? So if you're doing some sort of image classification, you take a pre-trained image net and then fine-tune the model on a specific task. This is how a lot of like modern machine learning goes, because you can take stuff that is generalizable to a lot of tasks and apply it to one specific task, just so you have a more generalizable model overall. But what's like a problem with normal MTL, right? Is that, so this is like a kind of a basic example is like, if you had a bunch of task specific models with parameters, like, by the way, these are all like matrices that represent the entire, like all the parameters in the model. What happens is generally you do something like an average, right? You average the model parameters across these task specific models. And you're kind of asserting that taking the average of the parameters will allow you to adapt well to multiple tasks. But that's not the case because you don't have like a very smooth landscape, right? So you have a very jagged landscape. So if you're like taking the average across multiple like hills, then if you take the average, it might actually be somewhere like higher in the loss landscape. And like you don't really have a rigorous or a robust explanation for why taking the average of these parameters will allow you to adapt well and fine tune, right? So we need some sort of pre-trained model whose optimization objective directly incorporates this quick adaptability to the tasks. And that's where MAML comes in, right? So MAML stands for Model-Agnostic Meta Learning, which basically provides an optimization objective that creates a pre-trained model that can easily fine-tune to unseen tasks. And yeah, this equation looks really complicated, but like I'll break it down in like the future slides. But this image on the right is important. It kind of explains how meta learning works. So you have this parameter theta, which is supposed to be optimized to like generalize well to unseen tasks. And then you have these 3 different tasks, 1, 2, and 3. And these are the optimal parameters for each one: theta 1 star, theta 2 star, theta 3 star. And these gradients take us in the direction of these different tasks. So you want to be in this state of being like over here, where within a few gradient descent update steps, you can get to any of these optimized parameters.
Wait, sorry, can you explain again like what those 3 are?
Yeah, so basically like these represent 3 different tasks. So theta stands for like a parameter matrix, right? So it represents like what are the parameters in the model. Theta 1 star is what are the optimal parameters for task 1, like let's say car versus truck classification. Theta 2 star is like apple versus orange classification. So that's what the theta 1 star and 2 star and 3 star represent. And then the gradient L1, gradient L2, gradient L3, those represent like the gradient update steps that you're taking.
Okay. So it chooses like for each task, it chooses like which parameters are, that's what that is.
Yeah. So MAML is trying to like basically be in the state over here. So that when you have like a specific task, you're kind of close to like theta 1 star, but you're also close to 2 star and 3 star. So then you can quickly like go to wherever you need to. Yeah.
I've always had a bit of a problem with this image. Do you mind if I like redraw it on the whiteboard real quick?
Yeah, go for
Just
it.
because I think the biggest issue is that like arrow should be pointing to the point where all the losses come out of.
Yeah.
I don't even need to redraw it, but yeah, like
Yeah.
like I think we're only witnessing one step here, right? Like theta 1 star is like, you know, the optimal parameters after one step of gradient descent, not like, you know, after n steps.
So where should it be then?
Like theta 1 star should be at the end of the gradient of L1.
Yeah, that's true. But yeah, and then this is the optimization objective, which I'll actually also get into the next slide. So yeah, before like all these symbols like scare you, let me like kind of go into what each of these symbols mean. So like in MAML and also in like other papers, you'll generally like kind of see a bunch of notation. So it's just kind of good to go over what that is. So you have some model f sub theta, which basically just represents, because a model at the end of the day is just a function, right? A model just maps a bunch of inputs to outputs. A function and maps an input to an output. So the model is parameterized by theta, and theta is like your like weights, right? Your weights and biases. So in this case, theta represents like a general set of parameters. But then theta I prime denotes the parameters updated for the I task through gradient update steps. So what that means is if you have, let's say, task 1, which is car versus truck classification, then from theta, it does a bunch of gradient update steps and it gets to theta 1 prime, which denotes like the optimal parameters needed to do car versus truck classification accurately. And then T is just a random variable whose state space is a set of tasks. So it's like basically just like the set of different tasks. And then P of T just represents the distribution of those tasks on T. So like with what probability you might want to do a specific task. And then each task T sub I has an associated loss function L sub T sub I. The reason why is because you can have like a classification task versus like a regression task. So you want different losses for that. And then F sub theta sub I prime is the model fine-tuned on task T sub I, because you take the parameters that are updated for the I task and then you apply that to the model, and now the model can do car versus truck classification accurately. So does anyone have any questions on like how like any of this notation? Okay, if not, now we can get to the scary part. So now like we'll take it one step at a time, right? So if we're given our MAML optimized parameters theta, so let's assume now like we don't know how MAML works. It gives us these like set of parameters theta, which we are told is able to easily adapt to specific tasks T sub I. And how we do that is by you have theta, you do a few gradient descent steps, right? All this is just like normal gradient descent. You have your theta, you have a learning rate alpha, you take the gradient with respect to theta, and then you do it of the loss for task I for f sub theta, right? So this is just normal gradient descent. You're updating theta to the specific task. And now this is our MAML optimization objective, right? Like every ML problem has the optimization objective. Like least squares is you're trying to minimize the L2 norm, right? Here, the objective is as follows. So you go over every single task T sub I in the space of tasks, and then you take the loss of that of the specific task with respect to the updated parameters, right? And remember, theta sub I prime is the parameters for a specific task. So it's like, let's say car versus truck classification. And this we already defined up here, right? So if you kind of fit that in, what you're actually like optimizing over is the loss with respect to the updated parameters, right? So you're not taking the loss with respect to theta, you're taking the loss with respect to theta after the gradient descent update has been done. So basically what ends up happening is you have this like meta optimization kind of, where through gradient descent, you take these steps because theta is like this thing that's already optimized to adapt to different tasks. And you take gradient descent update steps so that it like is so that it like generalizes well, right? Yeah, and notice the difference between like the first equation and the third one is that the first one is what you do in fine tuning, but the first one is what you do in pre-training. Yeah. So does anyone have any questions on this? On like any of this notation? Does it make sense? Yeah.
I mean, I get that this is a little bit different from just doing a weighted sum of the losses and then optimizing with respect to that.
Mhm.
Can you explain like how this is, like what's the intuitive difference? Because it seems like you're peaking one step in the future for each task. I don't quite get how that like is different from just taking a weighted sum of the losses for each task.
Yeah. So the thing is, now like in the optimization objective, you're including the fact that you can take gradient descent update steps. So keeping that in mind, like it's going to find a way that after like if like it's hard to, for example, do the gradient descent update steps in like the averaged parameter matrix, then it'll try to go towards something that even if it's not the average, even if it's like skewed towards one direction, that based on the loss landscape, it can quickly converge that. So that's basically why like the heart of MAML is like you're including the fact that you take these gradient like update steps in the like objective. Because if this is just f sub theta, then then you wouldn't really like you wouldn't really be doing that anything innovative. Because of this like second part over here where you're like including the fact that you can take gradient update steps, that's what makes it like difference.
Yeah, like one follow-up question to that.
Mhm.
I don't know. Why one step? It seems like
Yeah, so that's actually that's doesn't have to be one step. I think it's just like it's more so like the hype around the paper was that because it was able to do it in one step, it went from like not doing so basically I'll actually show a video later where like there's like an RL problem, you're having like this ant kind of move, and then within one gradient descent update step it went from like making random steps to like actually going like in the right direction. So you can actually extend that. So you can take like n gradient descent update steps, right? So that's like few shot learning versus one shot learning. But just so it doesn't really make the like this that different. You just like have multiple gradient descent update steps.
I guess another point to add to that is like the alpha they use in doing the peak is a different number than the actual learning rate, which is beta.
Yeah.
So you can like make the step very big, but it can do alpha.
Mm-hmm.
But it's still like a linear step.
Yeah. So one last thing, I wanted to track the like functional dependence here because we have a gradient with respect to theta of something that depends on theta in a pretty complex way, right? So I think this might be illuminating as to especially why it's hard to do like n steps in general or like train until convergence and then do it based on that. So we can get the the derivative of this loss function, right? And so we can bring this. You can imagine it's like just chain rule over and over again, right? So we'll end up with a derivative of this times like a gradient of this thing, right? And then we'll end up with this thing times a gradient of what's inside it. Gradient of this is just like, the matrix of ones, so that's easy. But what's the gradient with respect to theta of this thing, right? And like, correct me if I'm wrong, but does it turn out to be like a Jacobian of some sort, like a matrix?
Oh, like the actual like that I don't
like. I'm pretty sure you do have to construct like you have to do a second order method on this loss function in order to get like a Jacobian rather than just because like you have like double gradient here, right?
Yeah.
I imagine it would be close enough if they just pre-compute the theta i's and then like don't differentiate.
Wait, what's up?
I imagine it would be like close enough if they just pre-compute the theta i's and don't differentiate through it.
I'm not sure how it's done in the paper, but I want to say that when I've heard MAML like referenced with respect to like use in RL, for example, people will be like, oh, you have to construct it's like a second order method. You have to construct Jacobian for you have to do more than just like backprop on gradients. That being said, I mean, it's not hard for me to believe that, like, you know, by disregarding this gradient, you get pretty valuable results.
Yeah, I didn't look through the derivation of the paper that closely. I think I'll like take a second look after this, and I'll
No worries.
yeah.
But yeah, I mean, to answer Soham's question in a slightly different way, like perhaps if we do have to construct a Jacobian there, like you would end up having n.
Yeah.
I mean the Hessian, you're right.
Yeah, and so basically like because there are a lot of like different symbols here, there's one thing that you like if you take away that you should note is that here we have theta I prime and we don't have theta, right? So this is the actual MAML objective with theta I prime, but we might ask like why not just like directly optimize on f sub theta, right? So before like that, remember that theta represents like those generalized parameters that we fine tune on, whereas theta I prime represents the parameters for a specific task t sub I, right? So in the MAML objective, here we do f sub theta sub I prime, right? So we're doing this on the model that's fine-tuned to a specific task rather than the model that's like pre-trained, right? And the reason why we do this is that in the MAML objective, we have a pre-trained model and then fine-tuned to specific tasks. So we minimize with respect to parameters that we update a few times. So the thing is, this new objective is like kind of harder to fine tune in the sense that fine tuning is not accounted for in the optimization problem, right? Like here in the left, you're saying that I will fine tune in the future. So given that I'm going to fine tune to a specific task, can you find me a better like parameter matrix theta? But in the left, you're directly using theta, so you actually get worse performance, right? Like in the left, what you're actually doing is just doing normal multitask learning, and you're finding some like average parameter matrix data that you want to like do many different types of classification, right? Which will have some good accuracy, right? But MAML like extends upon that by in the objective directly stating that you can take gradient descent update steps, right? So there's a difference between using like the average parameter matrix and using that for all tasks, or having a pre-train and then fine tuning and then using it for that specific task.
Sorry,
Yeah.
you might have mentioned this, but is the right one just like averaging gradients? It seems like it is, right?
Yeah, it basically is. I think it's like it's still like slightly better than averaging gradients. I don't remember exactly why, but it's kind of like degenerates into that case.
Oh,
yeah.
I see.
Yeah. Yeah. So what are the benefits of MAML, right? Because this seems like kind of abstract. Like, how does this all fit in like it like into like the overall like field of meta learning, right? So the one benefit is this is effective for few shot learning, right? You only need a few training examples for task. And this is why I mentioned few shot learning before, is that if you're trying to train like car versus truck classification versus like cat versus dog classification, you only need a few images of cats and dogs, right? So you're kind of trying to extrapolate how as humans, we only need to look at a few cats and dogs to be able to classify thousands of them. And MAML is trying to do that same thing, right? You're trying to find that optimal like data that's like able to fine tune to different tasks. Also, it's fast in that you only need one or a few gradient update steps to fine tune to a specific task, right? So if you are like into NLP or CV, you might know that like you have this like this pre-trained model, like a pre-trained ImageNet, or you have a pre-trained like transformer, right? And then you have to do a lot of fine tuning, like you have to use a lot of compute power, data, and everything to fine tune onto a specific task. But with MAML, you have this like pre-trained model, and like within literally 1 or 2 or 3 gradient update steps, you have your fine-tuned model. So that's like the beauty of MAML. And the biggest thing is that there are no extra parameters, which is why it's like kind of big in research. So there are other algorithms that are similar to what we've seen in this paper, like for example, RL squared, which was actually made by BL2. And there are like similar algorithms that have been implemented before, but on RL squared, they use an entire extra set of parameters to be able to achieve this like generalization capability. But in MAML, no extra parameters are used at all, right? Because remember that what we do is we just have data and we directly just optimize to get the data sub I prime. So no extra space, no extra new parameter, like no new parameters are needed. And the other good thing is that MAML is just, it's a very general like algorithm, right? Like I didn't mention any specific model you had to use. So you can use a normal neural network, CNN, RNN, anything you want. Anything that updates via gradient descent is basically usable by MAML. And because of this, it's adaptable to supervised learning, reinforcement learning, etc., which will explain how you can like kind of fit MAML into those different like problems. Yeah, the only requirement is that the model optimizes on gradient descent. So first, how do we do MAML on supervised learning, right? Just to recall what is supervised learning, right? You have data points and you perform supervision, or sorry, it should be regression, not supervision. You either do regression or classification, right? Classification maps the inputs into a vector denoting, is it class 1, is it class 2, is it class n? Regression is it maps it into a real number. So what can you predict like what the price of a house is? So these are the objectives for regression and classification. This isn't really anything new. This is like just like regression, right? Is just like the L2 norm of like the difference between the ground truth and the actual prediction. And classification is like the cross entropy law. So this is nothing that new, but just so like you have it as reference to how like the MAML algorithm works, right? So for how MAML works for few-shot supervised learning is you sample a bunch of tasks, T sub I, from our like distribution P of T. You sample the data points needed for that task, and then you do this gradient update step for D and L sub T sub I, which is the loss for that specific task. And then you compute the updated parameters with gradient descent, and then you sample data points from T sub I for the meta update. And then after you run this loop for every single task, then you do this last step of like updating this data for like this is like remember that data is like the generalized parameters for across all the different tasks. And basically all this this looks pretty complicated, is just like what I mentioned in like this slide, how like we are trying to find a set of parameters that can adapt well to a bunch of tasks, and that's just applied to few-shot supervised learning. And yeah, the other thing is just like, is that it's few-shot, is that you only need a few training examples per task, and that this works well. And now for reinforcement learning is, how does this differ from supervised learning, right? Is that now you have trajectories, right? So if you're like a robot, you're state, action, state, action, state, action, right? And then you, these are called trajectories, right? The robot taking a certain path, and you have all these trajectories as different paths. And you're basically trying to find a policy, which if you don't know, RL policy is just, what do I do in a specific state? Like what action should I take in that state so I maximize my reward? And all of that is just encapsulated in this RL objective over here, just like the sum of the rewards. And then, yeah, notice how it's very similar for reinforcement learning. So that's like the cool thing about MAML, right? Is if you look at the previous slide, it's very identical for reinforcement learning and supervised learning. So instead of sampling data points, you sample trajectories. You do the exact same gradient descent updates for all the steps. And then it's basically the same otherwise. So that's like the cool thing about MAML. So a lot of what we've discussed so far is pretty abstract, right? So you might not really see like why this is cool. So now I'll kind of talk about like the experimental results of the paper and like their significance, right? So this is like one of the more basic tasks in the paper, and then I'll build up to the like more like cool tasks that they like work with. Is here they're just doing like a simple like they try to fit the best curve of best fit, right? So you have these triangles which represent the points that were given, and the red is the ground truth, right? So basically they're trying to model some sinusoid, and they're showing how for MAML versus pre-trained. Pre-trained is like the like previous state of the art, and then MAML is like the new state of the art. So for notice how for pre-trained, the like red, which is the actual ground truth, is very far from what the like what the actual models were predicted to be, right? So blue and so sorry, the blue is like the pre-update, and then these different dashed lines are like the model like converging into the optimal like optimal sinusoid. But notice how it's like very far, right? So with k equals 5, this is like the k-shot learning, right? So there's like 5 training examples, and this is like 10 training examples. And then notice, yeah, obviously for 10 training examples, it's slightly better, but still we're pretty far off from the curve because it's not able to generalize well. But now for MAML, notice how this green line, this green dashed line within 10 gradient descent update steps is much closer to the curve. And then once you have k equals 10, it almost exactly fits the curve, even for one gradient descent step. So that's basically like, this is like a very simple problem, right? Of like fitting a sinusoid to like the data points. And you can see how MAML like is able to fit the curve better than traditional methods. And then, yeah, this is just like showing how MAML beats the state of the art in all these different methods, which I won't really get into. Notice like we see things like Siamese nets and stuff, which are like few shot classification, like kind of benchmarks. Just like how in deep learning, you'll use like a very basic model to like use as like the baseline. The baseline here would be something like Siamese net. So to kind of see why this is like cool is so actually Bear has a blog by Chelsea Finn on this exact paper, and you can kind of see this working here. So this is let me go like task by task. So this task is half cheetah, which is basically you have this like this thing which is like a cheetah, and it has like these you're modeling these legs which are kind of like motors, and this cheetah is supposed to be able to like go forward and go backward, right? So notice how in zero gradient steps, it's kind of just like making random movements. It's not making any progress. But notice after doing one gradient descent step, it's able to move forward and it's able to move backward when you fine tune on those specific tasks. So just within one gradient descent step, you're able to have like an agent, which is this cheetah over here, to like be able to like do two completely different tasks just with one gradient descent step. So that's why MAML is like cool. And then just to like see, Ant is like a very similar task, but now you have like just a different robot. So notice how within zero, it's like kind of making random movements. It's not really making any progress. And then in one gradient descent step, it's like moving pretty quickly. And that's kind of like, this kind of encapsulates the beauty of MAML, is that within a few gradient descent steps, it's able to optimize to different tasks. Yeah, so now getting back to the presentation. Yeah, and that was just like what I mentioned here. These are just the graphs for it, but I won't really get into that. And yeah, so that is to kind of conclude everything that we learned today. We learned about like multitask learning, right? Which is the how like we have a model trained on multiple different tasks. Then you have few shot learning, which is that instead of thousands of training data points, you have just a few. So it's few shot learning. And MAML is basically an algorithm that allows us to make a pre-trained model that can quickly adapt to new tasks with a few gradient update steps. And it requires no new parameters, and you operate on a few training examples. And the key thing about MAML is that the objective function, so like the minimization objective, includes the fact that we fine-tune to tasks. So given this information, MAML tries to find a parameter matrix that can quickly adapt to different tasks instead of creating like an averaged model. And yeah, that basically brings us to the end of the presentation. Do you guys have any questions? Yeah. All right. Okay. Let's start. Hi, Usher.
Are you still at Krusty? Why is your camera off?
You can see, yeah.
That ain't
Hi.
If you want to see everyone, this is everyone.
Hello, everyone.
Yeah.
Nice talk.
Thank you. Okay.